Today we want to talk about significant figures and how we report values in science. Now, when we report values, we have to think about the accuracy and precision of those values. Now, sometimes those words are used kind of interchangeably in the English language in just regular talking, but in science they do not mean the same thing. Accuracy is how close a measurement gets or comes to the actual or true value. For instance, if the actual or true value was 2.10 grams when you were measuring some object, but when you measured 1.95 grams. That is an inaccurate measurement. It does not have accuracy. We're pretty familiar with accuracy. You either have the right value or you don't. However, there's another measure or another term that we look at whenever we're making measurements, because when you're making measurements, sometimes we don't know the actual value, and we'll do multiple trials. We'll measure an object several times to see if we come up with the same answer, the same measurement every time. And precision is how reproducible those measurements are. How close are they to each other? For instance, if I measured an object and the same object and I came up with 1.95 grams, 2.10 grams, and 2.38 grams. Well, for one thing, only one of those values is accurate. The other two are not accurate at all. And we should have very little faith that our measuring technique was very good, because they're all really far away from each other. So those three values we can't say that they're really accurate, and we definitely would say that they are not precise because they're not close to each other. But let's say that when we measure this object, we come up with the next time 1.95 grams, 1.94 grams, and 1.96 grams. Now we've got values that are quite close to each other. They're not still accurate, but they are very close to each other. We would say that those values are precise. They have good precision. They're close to each other. They may not be accurate. We can have precision and not be accurate. Now, what does that tell us? What it tells us is that our measuring technique is possibly good. It also could possibly be bad every single time. But it also could mean that the machine or that the measuring device we're using is not good also, that it's not calibrated correctly. So whether we're accurate or precise can give us a lot of information about our technique and about the instruments that we're using. So now let's say that we're going to make some measurements and we're going to report these values. And when we want to report values, we want to have measurements that are as exact as they can possibly be based on the device we're using to measure with, whether it's a balance or whether it's a ruler or a thermometer. We want to make those values as exact as possible. We want them to have as many significant figures as possible. So let's say I wanted to order carpet for a room, and I told the people on the phone that I wanted a piece of carpet that was 20 meters by 10 meters. Well, let's say this is really expensive carpet. And so they cut a 20 meter by 10 meter piece and they bring it to me, and what they find out is that the room was actually 20.4 meters by 10.2 meters. Is the piece of carpet going to be big enough? No, because those values are so inexact that we have a wide range of measurements that those could be rounded to. So we could take 20.4 meters and round it to 20. We could take 10.2 meters and round it to 10. But when we get that piece of carpet, it's not going to be the right size. So instead of sending them 20 by 10, let's say that I sent them 20.43 meters by 10.19 meters. Do you think that those people that are cutting that carpet are going to know they better cut that carpet at 20.43 meters and 10.19 meters exactly for that room? Yes. How exact you are is important. So how do we know how exact a number is? We know how exact a number is by how many sig figs it has. And the first step of that, and what we're going to be doing first today on this particular video, is simply figuring out how many sig figs a particular value has. And these are the rules that we use. All non-zero numbers are significant. So if we look at these example values down here, if all non-zero numbers are significant, then I could go through here on each one of these values and mark the non-zero numbers and know automatically that they are significant. So on this first example, I'm going to mark the 1 and the 2 because they are not zeros and therefore they are both significant digits. We always want to look at the next rule, a trapped zero. A zero is trapped. Primarily, the best way we can look at it is, does it have a sig fig on either side? If it has a sig fig on either side, then it's trapped. And zeros, let me tell you, are pesky little things to figure out if they are significant or not. So we really have to use these rules. So if we look at this value, is there a trapped zero here? Hopefully you picked this one. This one is a trapped zero because it has the 1 and the 2 on either side. It has a sig fig on either side, so it is trapped, therefore it's significant. It's the rest of the zeros then that give us a little bit of a headache. But the rules are not hard. You may have to keep referring back to them over and over at the first. You'll get, trust me, it's a little bit overwhelming, maybe a little bit at first, but you'll get used to this and it'll be super easy for you. When we look at the rest of the zeros, we need to decide if they are leading zeros or beginning zeros or ending zeros. If they are leading zeros, they are never ever significant. Now, what do I mean by leading zeros? Do you see an example here that has leading zeros? Hopefully you picked this one. Those are all leading zeros, and since they are all leading zeros, none of them are significant. Leading zeros are never significant no matter how many of them there are. The rule for ending zeros kind of has two parts. Ending zeros may or may not be significant, and it all depends on the decimal. If there is a decimal showing, ending zeros are significant. If there is no decimal showing, I mean, you may know there's a decimal there, but it's not showing, and if it's not showing, then those ending zeros are not significant. So let's look at this first example. There is an ending zero here. It's right here. And we have to decide if that ending zero is going to be significant or not. And we base it simply on, is there a decimal showing? Is there a decimal showing? The answer is, yep, there sure is right there. And if that decimal is showing, then that ending zero is significant. So this number has 4 sig figs. Look at the next one. The next one says, or first of all, just mark all of the automatically significant figures because they're not zeros. So hopefully you're marking the 4 and the 5. The next question you should ask yourself is there a trapped zero? No, there's not. There's not a trapped zero. There is a zero, and it has a sig fig on one side, that 5, but on the other side, there's nothing trapping it, so it is not trapped. So now we come down to the last two rules, whether it's a leading or an ending zero. There are no leading zeros. There are no zeros up here, but there is a zero at the end. And since there is an ending zero, we go with our rule. Ending zeros are only significant if there is a decimal showing. Is there a decimal showing? Yep, right there. Sig fig, 3 sig figs. The next one, once you mark out those leading zeros, pretty easy. There's only one value left, 1 sig fig. The next one, easy. The 1, the 5, and the 4, all non-zero digits, therefore they're all significant, so 3 sig figs for this value. The last two, similar numbers, but let's look at how this plays out. Look at the first one. Mark, well, you try those last two and see if you can follow the rules and come out with how many sig figs there are in each of those values. Hopefully you marked the 5 and the 4 in this one. Realize there were no beginning ones, so nothing at the beginning, so no leading zeros. There are no trapped zeros, but there are a bunch of ending zeros. Now, are those ending zeros significant? Hopefully you said no. And the reason you hopefully said no is because there is no decimal at the end. And since there is no decimal at the end, none of those zeros are significant. Therefore, this value only has 2 sig figs. What's the difference about the last one? If you look at this last one, you'll notice that, yes, it has a 9 and a 7 still are both significant because they're non-zero digits. But what about those ending zeros now? What makes them different? That little bitty dot right there makes them different because now we have a decimal showing. And if we have a decimal showing, what does that do to all of those zeros? Makes them significant. So unlike the number above it, which only had 2 sig figs, this one has 8. So we're going to conclude the video for this first part here with determining the number of sig figs. So if you'll do the worksheet, that first part where you're just determining sig figs, we'll come back then and look at how we know how to round different answer values to the correct number of sig figs.